Hey, it's Dr. J. How you doing today? We're going to learn about some applications of average value. So last time I showed you the formula or the recipe for average value. It starts with a function. It does have to be a continuous function, f, on the interval AB. So we start with a continuous function on the interval AB. The average is defined to be f_av 1 over b minus a times the integral from a to b of f of x dx. That's just a reminder of the recipe. We typically don't pay much attention to the fact that it has to be continuous. But if it wasn't continuous, so suppose a non-continuous function would just be a series of dots, you couldn't use the integral. You can't integrate a bunch of dots. You have to connect the dots with a continuous function, and then you can actually apply the integral. So as a conversation piece, we're not going to actually dive too deep into it. If you just had a bunch of dots, as long as you had a finite number of dots, you wouldn't need calculus to find the average. You would just add up all the values and divide by the number of dots. That would be the arithmetic mean from which this whole lesson began in part one, as sort of a background to where the average sort of started or where it came from. It's ancestry, so to speak. But we have continuous functions. Typically, they're curves. And so we're going to apply this to some applications. So the first application actually goes all the way back to the beginning of this course, compound interest. So suppose $8,000 is deposited into an account let's call it a savings account. Although it doesn't have to be a savings account. It could be an investment account. It could be a CD, secured deposit, certificate of deposit. It could be a loan. It could be the other way around. Instead of depositing the money, you could be borrowing the money. So the formula that I'm about to show you has lots of different applications, but I only have time to show you one. Let's do 4% annual interest. And we're going to compound continuously. All right. And since we're talking about average value, find the average value during the first 3 years. All right. So notice I gave this problem entirely in words. I mean, there's some numbers here, but you got to recall compounded continuously. A is a function of time. So instead of using x, we're going to use a variable t. You can switch variables. These variables do have to match. So whatever function, whatever independent variable you're using as your input to your function, the integration, you have to integrate with respect to that. So this is the integral with respect to t now. It's easy to fix. Just the x-axis becomes the t-axis. Is the principal, sorry, $8,000 times e to the rt. So our function is going to be $8,000 e to the 0.04t. There's our r. This is p, and there's r. All right. Now, in a basic math problem, basic algebra problem, I would just have you plug in 3 for t. All right, don't do that yet. All right. The 3 years is going to give us our interval AB. And because it's the first 3 years, the interval is going to be 0 to 3. I could ask more detailed questions if if we had another couple weeks just to talk about this. I could probably do several videos just on comparing different time intervals and what the results of these mean, and we could really dive deep into it. At this point in the course, we're getting very close to the end of the course, the end of the chapter. I just want you to see a few examples so that, mainly so that you can finish the homework and be prepared for the next test and the final. All right, so let's do the average value. Because our function is called a, it's AAV. You could call the function f if you want. It doesn't really matter. I'm just using the traditional name of it. So b minus a, so 1 over b minus a times the integral from 0 to 3 of 8,000 e to the 0.04 t dt. Remember, constants can come outside of the integral. And then 3 minus 0 is just 3. So that makes our integral a little easier to evaluate. I also wanted an excuse to cover some more integration techniques, or at least to review one of the integration techniques that we learned. So we're going to review really quickly U substitution, or U sub. So what we're going to do is we're going to let U be 0.04 t, and then du, this is a very easy one because the derivative of 4/100 times t is just 4/100 dt. Or if you prefer, the other way to do it is like this. I don't know how long it's been since you did this homework, but from a previous homework, it's the derivative of u with respect to t is just 0.4, and then you multiply both sides by dt. That's the sort of multi-step way to do it. And I actually like to go one more step. I like to divide both sides by 0.04. Why do I like to do this last step? Because it gives you a nice expression for dt. dt is du over 0.04. So this replaces the 0.04 t. I wish 8,000 was divisible by 3. I should have invested $9,000. It would have made this a lot easier. From 0 to 3 of e to the u. So my exponent has now been replaced with u. And then my dt is written du over 0.04. That decimal point got lost in there somewhere. 0.04. There we go. Or in other words, 8,000 over 3, 1 over 0.04 e to the u du. This is like an invisible 1, right here in front of the du. There's an invisible 1 right here. Well, there's another constant. Right? A constant can come outside of the integrand. So it's going to be 8,000 times 1 over 3 times 0.04 or 0.04. Now, all of that work to get to this step, now we're ready to integrate. So all that work right there was just to get rid of that decimal up in the exponent. Because I don't have an antiderivative or an indefinite integral, or in this case, a definite integral for e to some decimal power, but I do have one for e. Remember, e is just e. The integral, the antiderivative of e is equal to e. Also, the derivative of e is just e. It doesn't matter whether the variable is u or whether the variable is x. Those things are equal. E is that very special number that we like to use, special base. All right, let's clean this up a little bit. Got my calculator handy. I probably don't need it yet, but let's see. 8,000 times 1 is 8,000, and 3 times 0.04 is 0.12. Integral from 0 to 3 of e to the u du. Now I got my antiderivative here. Oh, let's go ahead and do this while we're at it. If it comes out nice, 8,000 divided by 0.12. Oh, that sucks. 66666. I must have made a deal with the devil. 66667. Blah, 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 blah. I'll probably round this eventually, but let's just leave it like that for now. I'm kind of regretting that, but that's okay. If I can always go back and fix that if I have to. Add more decimals if necessary. On the calculator, just goes on forever. All right, so now the antiderivative of e to the u is just e to the u. But then remember, u was 0.04 t. So I got 66666. If I'm really concerned about this, I can write it as 2/3 if I really want to be safe. I don't think it's going to matter. But I'm always worried about losing a decimal and then my answer being slightly off. And I've got a long, history, even just in this class, 3 months of making tiny little mistakes that I end up regretting. All right, so now I want to do the antiderivative from 0 to 3. I'm going to evaluate it. But remember, I got to put my t back in before I evaluate my boundaries. The other method is to change the boundaries using the u, but I mean, why do that? If I change the boundaries, it'll change sort of the nature of my understanding of the problem. I still want it to say 3 years, right? Although theoretically you could change those and you would still get the same result, but you might not interpret it correctly. And then now the easy part is just plugging in the 3. So when we plug in the 3 into the t, we get e to the 0.12. And then when we plug in the 0, we get e to the 0. Right? 0 times 400ths is still just 0. And exponential button on the calculator gives us decimals. See, I don't know what I was worried about with these fractions. I was going to end up with decimals anyway. So yeah, I've just put my 2/3 back to being a decimal. Irrational fear of decimals unless they terminate. So this one's kind of ugly. It's an irrational decimal. It does not terminate. It does not repeat. And then e to the 0 is just 1. So -1 there. I might as well just do that while I have it up on the calculator. I'm just going to minus the 1 right now. Oh, and I might as well multiply these as well. If you keep everything on the calculator, you don't have to worry about being off. And then I'm going to multiply times 66666. 5 6 is 667. So times 66,666 and 66 cents. And I'm going to round to the nearest dollar anyway. So this is 8,499.79 or 8,500. $8,500. 79 cents rounds up to a whole dollar, and then the $4.99 rounds up to $500. I don't need to tell you that. So the average value is $8,500. Now, let's think about this for a minute before we move on to the next question. It's $8,500, right? Or in words, I'm using a dollar symbol, or I could write it out in unit words, dollars. Now, this is an average, right? Think about other averages that we've done, right? If you think back to this course, you've been watching these videos for 3 months now. In the past, an average was a rate, right? It would say, dollars per day, right? On average, we spent $5 a day, or when we're going to get deeper into the revenue and the cost problems, we'd say, oh, we made, $6 per unit, right? We're measuring the number of units or gadgets or gizmos or whatever it is that this business model was modeling. This type of average is just a value. That's why it's called average value. It's not a rate. So it's a different type of use of the word average, right? If you remember, if I said, F hat, yeah, this type of average would be f of x divided by x. This is a rate average, right? Or we had the AROC, f of b minus f of a over b minus a. This also told us the average, but these were all in terms of rates. It would say, you're spending $20 per day, or you're making $500 per unit. There was always a per involved in there. This does not have that. Average value simply gives you a unit value in the number of whatever units we're measuring in. In this case, we're measuring in dollars. So the answer is $8,500. So where does the time go? Oh, what a question that is. Oh, I wish I could tell you. Where does the time go? Well, I don't know the answer in life. But in math, I know exactly where the time goes. The time is t, yeah? And it's involved in the answer as an interval. So the interval is 0 to 3. It's implied. So when I say that the average is $8,500, right, it's not static. It's not like the $8,500 is just sitting there. Yeah. It's saying that over the course of 3 years, the average is $8,500, right? But it's not $8,500 per year, right? And it's not even $8,500 per 3 years. What it really means is that at any given time, any moment in time, yeah, I would say that we have $8,500 in the bank. And we might have more, we might have less. But if somebody were to ask you, well, how much do you have in the bank? And you don't actually want to go check your balance, right, on that at that particular moment, as long as it's within this 3-year period, somewhere within this 3-year period, that's what the number means. You've probably had enough of me talking about this, but I'm going to get a lot of answers today, and I want to just make sure that not only is it important that you get the right answer, but for your lifetime longevity and career and future education, that the number is more than simply a green check mark, a green box that gets checked, and that it actually means something. I often overlook these things myself. I'll just do a math problem, I'll get an answer, and I'll move on to the next problem. And so I'm encouraging you to slow down and smell the dollars. Smell the roses. The roses aren't free. Let's do another one. So a company predicts weekly sales T weeks after online sales began by the model S of T, the sales in terms of time. And let's do another exponential, e to the negative 0.02t. I'm going to do the problem before I talk any more about what it actually means. Let's just do the problem. Find the sales average over the first 8 weeks. Maybe I'll draw a picture and show you what the area actually looks like. I didn't bother drawing a picture with the last one. Spoiler alert, it's a curve. All right, now this one is a similar curve, but opposite direction. This one's going to go down. It's going to be a decreasing. So the sales for this company not looking very good. Right? Each week you're selling less and less and less. I'm not going to get into the hows and whys of that is. So the first 8 weeks, our interval is 0 to 8. So SAV is 1 over 8 minus 0 times the integral from 0 to 8. You might have noticed last time I did all that U substitution stuff. I'm going to pull out the 700, put it on top here. So this is a little bit tricky. We're going to do the same technique, but we can kind of just recall that if U is negative 0.02t, then dt is du over negative 0.002. Right? In other words, taking the derivative and then dividing. Oh, I got one too many zeros. Taking the derivative and dividing by the constant here, the decimal. This little recall here is all of the steps that I showed in example 1 for finding the substitution. And then this gives us, if you remember this technique, you'll see that it comes in handy. You can very quickly replace this with U. Let's see if 700 is nicely divisible by 8. Not too bad. 87.5. That's nice. All right. Oh, dt. Almost forgot my dt. If you do forget your dt, when you get to this substituting step, you're going to need it. So that'll give you a chance to go back and pick it up. So the exponent becomes u, and then the dt becomes du over negative 0.02. And you might notice a very similar pattern to what happened last time. So I've got 87.5 times the integral of 1 over negative 0.02 e to the u du. So remember, there's an invisible 1 here. So it's 1 over this decimal. And then I'm going to pull it out. So it's 87.5 over negative 0.02 times the integral from 0 to 8. Oh, don't you just wish every function was the e? It's one of the reasons why we use it so often in modeling. 87.5 divided by 0.02 negative 4,375. Now that, remember, the antiderivative of e is just e again. Now here's the mistake that I always made when I was young, inexperienced, or even old and lazy. Either one. Both events cause the same kind of error. And that's to simply plug in 8 and plug in 0. It drives me crazy because I don't get the right answer and I can't figure out what I did wrong. You've got to switch back. These represent time, the 0 month and the 8th month. You got to switch back before you plug in your time. So switch back to t's, and now you can plug in your value. All right, one of them is going to be nice. The other one, not so much. Let's see. So we got 0.02, negative 0.02, and I'm going to plug in 8, so times 8. So I've got e to the negative 16 hundredths minus e to the 0. Yeah, that when I plug in 0, that one's easy. I'm going to keep this on my calculator and then do my e. So negative 4,375. I like to write everything down. Doesn't mean I'm not going to make any mistakes, but at least if I make one, I can find where it is. And if you find one, you can tell me where it is by having written all this down. Thank you for your diligence in finding my errors when I make them. And so this, I like to just keep the whole number on the screen and then multiply by, oh, actually, let's subtract 1 first. You could distribute, by the way. That I'm just not going to do that, though. I like to just do it this way. It's up to you. I'm going to subtract 1 first. And then I get negative 4375. Why do I do that? Because the constant on the outside is easy to track, until the very last step. And if I don't end up with a negative times a negative, I know I did something wrong. Because again, this is a value. It's a quantity, right? I mean, the only quantity that can be negative is profit, right? Can't have negative sales, right? You can have negative profit, though. So when we get to profit, we could end up with negative numbers. But if we get negative numbers any time before that, then we know we made a mistake. Times 4375. You might say, well, you can have negative cost. Well, sort of. And we're going to round to the nearest dollar again. So that's approximately $647. There we go. Sometimes I ask for the nearest cent. I don't what motivated me to do dollars here. I think if it's sales and I'm just going to tell my boss how much money we're making, they don't care about the 87 cents. They just care about the dollars. And again, this is not dollars per week. And I have to admit, when I first read this problem, My initial instinct was to answer, "Oh, on average you're selling $647." No, that's not what this means. This means over the course of 8 weeks, right? Over the course of 8 weeks, the average is $647. Total sales. Not sales per week, but total. Sometimes the picture actually helps. Helps kind of motivate. Right? Here's 0, here's 8. Well, what do we start at? 700? So 700 was the launch, right? And then what happens is this company's not doing so hot. Immediately their sales dip right out of the gate, right? So something's wrong. Maybe they're not advertising properly, or maybe their product sucks, right? I don't know. Whatever it is. I'm not going to get all into the social science, of why and how it's doing badly, right? And so the average is sort of somewhere here. I call it SAV, $647. And so it's like all of these sales that we had here will match here, right? And essentially, over the course of 8 weeks, we just had a rectangle where 647 is the ceiling. Yeah. So basically, at any given time, so this number means at any time during the 8 weeks, sales are $647. At any time in here. So how much are we selling, boss? $647. How much are we selling now? $647. How much are we selling now? $647. At any time. So that's kind of the idea behind the average value. It just gives you a number. It just gives you a unit. Right? It's like, imagine a bar graph. I like to go back to the Riemann sum, in which all of the rectangles are exactly the same height. All right, so that's the idea behind the average value. We did talk about the mean value theorem. There is a point somewhere in here. I'm not going to ask you to find it today. I honestly don't care anymore. It was more of an academic, abstract concept thing. But there was a time somewhere between 0 and 8, and it's probably not a whole number. So it's probably somewhere in the middle, at 12:30, whatever, on whatever day, the sales were exactly $647. Exactly that moment. All right. That's enough about sales. So you got to sell stuff, but you got to buy stuff too, right? So next we're going to talk about cost. And this is where it really gets fun. The cost to manufacture X units of a particular product, I don't care what it is given by a C of X function, a cost function. Now, most of the cost functions that we've seen have been pretty tame, but now that we're towards the end of the course, we're going to have some more elaborate cost functions. If you want to think about what this means, it's kind of like the cost is expensive in the beginning, right? It's got a flat cost of $185, right? And instead of just constantly going up at the same rate, like that would be a nice linear, very simple cost function that we've seen in the past. As you buy more units, it gets cheaper and cheaper and cheaper for each additional unit. So if you remember the section on derivatives and the margins, we talked about the marginal cost. The marginal cost here was much higher than the marginal cost here. The slope here is steeper, yeah, because we're making less units. But if we're making, if we have like, 5,000 units, and then we just want to make one additional unit, remember the margin is the cost to increase one, how much it costs to produce one more unit would be very, very small, right? It's very flat, yeah. Right, so that's sort of a marginal analysis and just a geometric idea. And again, X is like, the number of units. Now, that's just to give you an idea of what this function represents, right? So I'd like you to be able to solve the problem with some background. I want you to find the total cost average to produce between 0 and 30 units. Now this is going to be especially tricky for the final, because in the final you might have average cost and total cost average. This is not the same as average cost. That's very important. And there might be two questions on the final that have the word average in them, and they don't necessarily mean the same thing. Average cost is this. Yeah. This is a rate per unit. So average cost is the thing with the hat on the top of it. And we say, oh, the average cost says, how much is it costing me to produce each unit? That's on average, right? This is not asking that. This is total cost average. So anywhere between 0 and 30 units, so my interval is 0 to 30, I don't want to find the cost to produce one unit, which is what this function does, the C hat. I want to do C av, which, it uses the same word, but it means something different. Let's calculate it, and I'll explain how it's not a rate. It's not telling me how much per unit. It's telling me the total on this interval. So again, 1 over 30 minus 0, same old story, 0 to 30. I have to do some examples where we don't start at 0, just to round this lecture off. But for now, they're all starting. And then we'll take our cost function, 185. I better use some parentheses. Plus 45 times the square root of 5x dx. Well, let's do the easy stuff first. 1 over 30. The integral from 0 to 30 of 185. Here, let's use some brackets here. And then another integral from 0 to 30 of 45. So I'm going to break up the sum of the integrals as the integral of the sum. I'm going to break it up into the sum of the integrals. Why am I doing that? Because this first one is going to be very, very easy, and I just want to knock it out and have it be done with it. So this is 1 over 30 times the integral. What's the antiderivative of 185? So I can squeeze it in here. I'm going to dispense with this one first. And then I'm going to rewrite it at the top if the video is cutting this off here. I'll rewrite it. So the integral here is very easy. It's just 185x. All right. This one, on the other hand, I'm going to need a u sub. So we'll come up here and do that. So I've got 1 over 30 times 185x plus, I'm just going to copy the whole thing, 0 to 30, 45 square root of 5x dx. So I really don't want these mixing with each other. So that's why I separated them out. So this one's done. I've already done the antiderivative. I haven't plugged in the numbers yet, but I'll do that later. All right. I'll plug in the 0 and the 30 at the end. You might want, if you need to, put a little note to yourself, plug in 0, plug in 30. You could do it now and get it over with, but I'm just going to wait. I'm going to do all my plugging in at the end. All right, so what's the U sub for this one? What's the U substitution? Well, the first thing I want to think about is the square root. I do know how to find the antiderivative of the square root, but I don't know how to find the antiderivative of the square root of 5x. So I'm going to say, well, that means that dx is du over 5. Just divide both sides by 5. And then take the derivative. Again, this is a very, very simple form of differentiation as it applies to the integral. I can also pull the 45 out. And so instead of integrating 5x, I can integrate u, right? Square root of u. And then instead of having my variable of integration be dx, I can have it be du. du over 5. And this is the same as 1/5, right? So 1 over 30 times, I've already integrated 185x plus 45 and 1/5 is just going to be 9. All right. It's the same as 45 times 1/5. And then I've got the integral from 0 to 30 of u to 0 to 30 of u to the 1/2 du. (185x) plus 9. Now we have to remember the rules of integration, which is add and then divide. Yeah. Add 1 and then divide by the result. So 3/2. And then here's my reminder. It's really just a reminder that you have to still plug in the boundaries. There are other ways to notate that. One clever way is to go t equals 30, t equals 0. Takes a little extra writing, but it'll keep you from making that rookie mistake that I've made even as a pro. And even when you turn pro, you still sometimes make rookie mistakes. And I'm also going to get rid of the 3/2. That's going to be 9 divided by 3 times 2. So 9 divided by 3 is 3. 3 times 2 is 6. And then I'm going to put the u back. That's going to be 5x to the 3/2. Right? And if you mark them off as t's, oh, they're not t's, by the way. I don't know why I said t. I know why, because time. But we're not doing time, we're doing units. Not time. We were doing time in the last example. All right, now we're ready to plug in our units. So this is it. This is now just algebra. Plug everybody in. And this is our total cost average. CAV. So it's 1/30th times 185 times 30 plus 6 times the square root of 5 times 30 cubed. Yeah, square root cubed. And then minus 0. That's nice. When you plug in 0 into this, both of these terms turn into 0. So it's not like with the E. With the E, when you plug in 0, you get 1. But with this function, when you plug in 0, you're just going to get 0. All right, there we go. Now it's all calculator work. So what do we got? 185 times 30. That's 55, 5,550. Make sure the 6 does not multiply by the 5. I have seen that mistake before. You get 30 times 30, and then you do 30 square root, or 30 squared, and then square root, and the whole thing ends up all messed up. So it's 5 times 30, which I don't really need a calculator for, but I did it anyway, 150. Then the square root, right? Then cube it, and then times 6. 11,022.70 cents. Oh, this one actually says round to the nearest cent. So I'm going to go a little extra. 73.84. When you want to round to the nearest cent, go a little bit further, just a couple digits further, so that you don't end up with error. All right. Or you could have no error by just keeping all the numbers on your calculator. Plus 5550, and then divided by 30. I get 552.42. This is dollars. It is dollars that are rounded to the nearest cent. All right. And again, it's not dollars per unit. I had a tough time with this as a student, and honestly, even as a professor, when I'm explaining it. Because you might think, oh, it's costing me $550. You report this to somebody, you give them the number. They, really? It's costing me $500. That's the average? $552 per unit? No. That's not what it means. Again, let's explain what it means now. If X is the number of units, and then here's your cost function, and you're between 0 and 30, and you've got this average, say right here, 552 and 42 cents, but I'm done with the problem now, so I can just draw the picture. And the average is going through here. It's saying that anywhere between 0 and 30 units, if my production is between 0 and 30 units, anywhere between 0 and 30 units, the total cost, not per unit, but the total cost is $552.42. It's essentially homogenizing production and saying, imagine that everything costs the same amount, right? Then what would that be? All right. If you did the hat, the C hat, I'll leave this as a DIY. I don't have time to do it. Compare just for fun. It'd be a nice practice for the final anyway, right? Because on the final exam, there might be some problems that ask you for average cost as opposed to cost average. They don't mean the same thing. Average cost is telling you how much each individual unit is costing. Right? How much is this one? How much is that one? How much is that one? The total cost is basically a giant rectangle of the total cost average. It's ignoring the curvature and just saying if everything costs the same amount, then this is how much your total would be to produce anywhere in that area, in that region. All right. So the interpretation, I think, takes a little bit of wrapping your mind around to really understand what your answer means. Okay. You will find that if you do this DIY, do-it-yourself problem, you will not get $552.42. All right. I'll tell you that right now. You will get a much smaller number, and it basically tells you the cost of each individual unit, whatever these things happen to be. Okay, ready to finish this up? All right, example 4. So suppose we only have the marginal revenue. Review of chapter 2. I'm not going to do all the steps to get it. So suppose that you already have done the steps and you have the marginal revenue, which is the derivative of the revenue function. Okay, it's a very simple one. All right, so this one will probably go pretty easily. And then I'll explain sort of what the result is. I want you to compare. Well, first find them. Find the average marginal revenue for the first 20 units. Then find the average marginal revenue when between 21 and 41 units are sold. Oh, the first 20 units are also sold. Obviously, it's revenue, so we're just selling these things. We're not worrying about how much it costs to produce them. It's sort of a two-part question. You could also phrase it, find the marginal revenue, the average marginal revenue, AMR, first 20 units, and I could say find average marginal revenue, AMR, for the second 20 units. Why didn't I say that? Well, I did it that way, and oftentimes you'll do 20 to 40, right? It's pretty common. First 20, second 20, right? It's pretty common. 0 to 20, and then 20 to 40. But the second 20 actually starts with 21, right? So it's a slight technicality. And what's interesting is the first 20 starts with 0. I find that quite interesting. It doesn't start with 1. It starts with 0. That's because the formula requires that you go. All right. So AMR is also known as R prime AV, average marginal revenue, AMR. The formula requires that you go A to B. Right? It's all dressed up in the recipe. And if you go from 1 to 20, watch what would happen. You would end up dividing by 19 units. But it's not 19 units, it's 20 units. So that's why we actually start at 0. So that you end up dividing, 1 divided by 20. So it's a solid 20 units. And then the revenue function is negative 0.2x plus 250 with respect to x. This one's going to be smooth. I don't even need to do any fancy substitutions. I can just take the antiderivatives. Antiderivative of x is x squared over 2. Divide the constant by 2 here. Antiderivative of 250 is 250x. I didn't have to do any substitutions. I just go from 0 to 20. So r hat av from 0 to 20 is 1/20 times negative 0.1 times 20 squared. Right, I'm plugging in 20. I'm also simplifying the constant. Plus 250 times 20 minus 0. Because this is a polynomial, right? When you plug in, it's a polynomial with no constant term. Everybody has an x. When you plug in 0 in for x, you're just going to get 0. Right. That's mainly just for your notes. So you know that I actually did plug in 0. I got 0 when I did it. And then now do the whole thing on the calculator. 1 over 20 times negative 40. I did that in my head. Let me make sure it's right. 20 squared is 400 times negative 0.1 is negative 40. Just making sure, right? And then 2,500 times 20, I believe, is 5,000. 250, did I say 2,500? I meant 250 times 20 is 5,000. All right. So that's going to be 1/20 times 4,600. 4,600 divided by 20 is $230. So that's what we call AMR first 20. All right, average marginal revenue to sell the first 20 units. All right. Now let's sell the second 20 units. And again, we're going between 21 and 41 for a couple of reasons. That's 20 units, primarily, right? It's not from 20 to 40, although that would also be 20 units. But then that would mean the first 20 were actually the first 19, right? So I'm trying to do 20 units and then another solid 20 units. So when I do the average, all I have to change now is the boundaries from 21 to 41. So I'm going to kind of get a redo here. So now I'm between 21 and 41 units. I already have all this work here. AMR, R prime AV, right? Average marginal revenue. And I'm just changing the boundaries. So this is now going to be 41, and this is going to be 21. Unfortunately, if one of the boundaries is not 0, you're going to have to pay attention to both of them. All right. Let me copy this down because I'm going to have to erase it. So over here out of sight, I'll put 230 AMR first 20. Just to remind myself that I already had an answer there. All right. I've got my antiderivatives exactly the same. I'm just changing the boundaries now. So now I'm going to do 41 units. Now I got to be careful because I'm not subtracting nothing. I'm subtracting, and then I have to now do 21 units. So double negative there. All right, let's let the calculator do the work. So I've got 41 squared times 0.1 negative. So that's negative 168.1. Got 250 times 41 units. 10,250. I'm a little paranoid of making mistakes, so let me double check that. Yep, 10,000. Now this is going to be a negative, so that's going to be a positive. 21 squared times 0.1. So 44.1. And then that's going to be a negative times a positive. So that's going to be a negative 21 times 250. 5250. You could distribute the 1 over 20. I don't find it any easier. I just find it easier just to go through all these. Oh, it's negative 5250. And then plus 44.1. So I'm just adding up the dollars. Plus 10,250. Minus $168.10. So I get 4876, and then I'm going to divide that by 20. 243.8, or $243.80. Now, normally, I would say this is $243.80 solid, right? It's not a rate. But because it's a margin, it's an average marginal revenue. Yeah. Because the margin is a rate. Right? A margin is a rate. It's a derivative. That's what, in fancy business terms, we call it a margin, right? But it's marginal revenue is a rate. It's the derivative, yeah. And so this is dollars per unit. It's not just dollars anymore. Yeah. So, and it's because the function of which we are finding the average is in itself a rate. Yeah. Now let's compare this. This is for the second 20, right? So in other words, between 21 and 41, right? The first 20, 0 to 20, the AMR was 230 and no cents. So when we compare these two, what's happening? Clearly, revenue is increasing, right? Why is that important? Well, remember, the average is saying anywhere in this range, right? Anywhere in this range, the average is $243.80 per unit, yeah? But if you're in the lower range, from 0 to 20, you're only making $230 per unit, right? So when you're analyzing a revenue model, you want to think of all possibilities in that range of units. Yeah. So again, this 230 is not, it's an average for anywhere in that range. Yeah. And then when you go to the next range between 21 and 41 units, your average goes up to 243. So that means our revenue is increasing. If this was going down, then that means you're on the other side of the hump. Right? So this basically tells you what side of the hump you're on. If the revenue is increasing, then that means we're on this side of the hump. We have not yet reached our maximum yet. Once you reach the maximum revenue, this will turn around and go the other way. And the next 20 units would actually decrease the revenue. So this is a way of analyzing your revenue model in terms of intervals, right? So, okay, how much is it changing on this interval? How much is it changing on this interval? I will make a comment before I do the last example today. So comment, R prime av is not the same as R hat prime. These are different. These are different. R prime av is called map. So, sorry, it's called AMP, average marginal revenue. R hat prime is called MAP, marginal average revenue. And they do not measure the same thing. Okay. Just want to make that comment because in the next example, I might ask for both. But I've already done cost, I've already done revenue, so let's move on to profit. So the cost to make a particular unit, to make X units of a particular product. Let's do a nice simple linear cost model to kind of wrap this up. And the price demand negative 0.06x. You notice that price demand looks a heck of a lot like marginal revenue. Yeah. In fact, it is. Oh, sorry. I don't know why I wrote the word demand and then I actually. You can use the letter D for demand too, you know, but because it's price demand, it's better to use P because it doesn't tell you the demand, it tells you the price. You can use the letter D for demand, but you better be very careful with what context you're using the letter D in. I might do that in the final section. We talk about supply and demand. But all right, we're going to wrap this up. Find the average marginal profit when 107 units are produced and sold. All right. I'm assuming it's the first. I mean, if I don't indicate it's the first, you assume it's the first 107 units. Right. And then, well, let's just do that first. And then I'll switch up the words and I'll do marginal average profit, MAP, as opposed to AMP. So this is AMP, AMP. You could do the same thing for revenue. I'm not going to. I think this video has already gone on long enough, so I want to wrap this up. So we have to find the profit function. That's going to be the revenue minus the cost. Remember, revenue is just P of X times X So just multiply this whole thing by x. So you get a revenue function. So that's revenue. Minus the cost, 14x plus 195. So our profit function is negative 0.06x squared plus 27x minus 14x minus 195. This negative, of course, distributes just like it always did. Make sure you combine the similar terms or the like terms. 27 minus 14 is 13x minus 195. All right, so that's our profit model. And now we're going to produce and sell the first 107 units and find the AMP, the AMP. Or you could call this P-AV. No, P prime av. So we need P prime first. We're not ready to find the amp yet because we don't have the M, average margin. So first we need the margin. So now we take the derivative. Notice the 195 goes away when you take the derivative. The derivative of negative 195 is 0. 2 times 6 hundredths is 12 hundredths, or 0.12. And now we can do the amp, or P hat av, or P prime av, sorry, not hat. I'll do hat later. That'll be 1 over 107, or 1 over 107 minus 0 times the integral from 0 to 107 of negative 0.12. Doesn't this just look just like the revenue function? That's when you start taking these margins of profit, you end up with something that looks exactly like revenue. The key difference is, look, the revenue is 27x, and then the profit is only 13x because you subtracted the cost. All right. Fixed cost was 195. That did not affect the margin. You probably noticed that back in chapter 2 when we were first doing marginal analysis. So if you didn't notice it then now would be a great time to notice it. Again, these ones are all set up so that the integrals themselves are rather easy. So it's going to be negative 0.12x squared over 2 plus 13x from 0 to 107. If you want to simplify that, you can. I'm just going to do it all at once. So plug in 107, and then I'll do all the simplifying. So 107 squared, it's 11,449. I'm going to do it all at once. Divided by 2 times 0.12. I guess I could have simplified that. It would have gone back to being 0.6. I think that's interesting. 0.06, sorry. All right, and then it's negative. And then here I got 13 times 107, 13 times 107 units, 1391. And then I'm going to subtract this, 686.94, 704, and then I'm going to divide by 107. $6.58. So I got P prime av is 6.58. It's also known as the average marginal profit, AMP. So, well, I've kind of been alluding to this the whole time. What is MAP? Marginal average profit. It's a completely different thing. Yeah, it's a completely different thing. You don't do an integral at all. No integral for this. First, you find the average profit. Average profit was also known as P hat. Okay, it's divided by X. Then you take the derivative Now remember, the derivative of negative 0.6x is negative 0.6. The derivative of 13 is 0. And the derivative of negative 195 over x changes to positive. Yeah, it's a negative times a negative. Sometimes it's helpful to write it this way. Instead of over x, put x to the negative 1. And then when you multiply, negative times a negative turns to positive, and then the power goes to x squared. I don't want the computer to die on this very last example. All right. And then you plug in 107. You don't have to take an integral to do the map. You have to do the marginal average profit. You have to do an integral to do the AMP, the average marginal profit. And let's see the difference. If I'm running out of room here, I'll try to put it up here. So I've got 107 squared, and then 195 divided by that. All right, so that's 195 divided by 107 squared, and then plus negative 0.06. I can just go minus 0.06, and I get negative 0.04. I'm rounding to the nearest cent. All right, so I just plugged in 107 in this for x, and that gives me my marginal average profit. And notice the difference between these numbers, right? Again, this represents an area, so to speak. Well, it's an area divided by the width. Yeah. So if you think about the results of this, this is sort of the rate of change of the average, right? So we're saying that the average profit per unit is decreasing by 4 cents. Yeah. So every time I sell another, I make another, I have to make it, then I have to sell it. And then every time, remember this is for 107 units. So at this point, the average profit per unit is decreasing. That's what the map tells you. The amp tells you something else, right? This tells you that when between 0 and 107 units are produced and sold, all right, you got to produce it and sell it. The marginal profit for each unit is $6.58. So even though the profit is decreasing, so I'm on this side of the profit curve, yeah, that's what the map tells you. I'm losing money every time, yeah, but I'm still making a profit. I'm not in the red yet. So I'm still above ground. I'm making, on average, right? And again, it's on average, anywhere between 0 and 107 units. On average, I'm making $6.58 per unit. All right. So AMP refers to the average profit gain from selling one additional unit across this whole range from 0 to 107. MAP means the change in average profit, how much it's changing, and it's changing by decreasing by 4 cents. Okay, so I hope that was helpful. It's a lot. That's why I sort of singled out a few specific types of problems that I'd want you to know how to do. We could get into the weeds with lots of scenarios, but that would be a topic for outside of this video if you wanted to discuss that in more detail, or possibly topics that you might see in economics or in a more business specific area. For calculus, I just want you to be able to take a derivative or take an integral, and also understand which is which, and that's about where I'll end. So until we meet again, keep doing your homework. I'm Dr. Jordan, and I'll see you on the internet.